Well, welcome to, what is it, day 3 of our conference. So Alexey Ananyevskiy will speak on the A1-Euler characteristic of the variety of maximal tori.
Yeah, thank you. Just to check, you can see my notes, right?
Yes.
Okay. So thank you for the invitation and for giving me an opportunity to speak here. I will talk on the A1 Euler characteristic, and I will start with some general nonsense related to Euler characteristic, which probably most of you know, but yeah, in any case, I will repeat it. So one can define the notion of Euler characteristic in an arbitrary symmetric monoidal category. So let's have a symmetric monoidal category. And you can define this notion for strongly dualizable objects. Let me recall that an object is strongly dualizable if there is a dual object, right? And the morphers which make this object dual of X. So morphisms, coevaluation from the unit of this monoidal category to X wedge X dual, and the evaluation from X dual wedge X to 1. And an easy example to keep in mind is to look at the finite dimensional or infinite dimensional vector spaces, and the evaluation is just evaluation of the function, and X dual is of course the dual space. Evaluation is the evaluation of the function on the vector, and coevaluation is a kind of a diagonal matrix, something like that. So there should be such morphisms, and then of course they should satisfy some relations, the usual ones. So if you start with X, which is the same as 1 wedge X, from here we can go to X wedge X dual wedge X, and this is coevaluation wedge ID. And then we can evaluate on the second and third factors. So go to X wedge 1 via ID slash evaluation, which is the same as X. And this map should be identity. And this is the first relation that we need, and the same for X dual. So X dual smash 1 goes to X dual smash X dual, and then 1 smash X dual, which is the same as X dual, and this should be identity. Yes, and an object such that this stuff exists is called strongly dualizable. And this dual object and these morphisms are, if they exist, they are unique up to isomorphism. So then for strongly dualizable objects, one can define the notion of Euler characteristic. So again, we are in a symmetric monoidal category. And we have a dualizable object, strongly dualizable. Then the Euler characteristic is defined as follows. First, we take the coevaluation map, and then we switch the factors using symmetric structure on this monoidal category. And then we evaluate. So this gives us a map from the unit to the unit. And this map is called the Euler characteristic of X in this category C. And this Euler characteristic is an endomorphism, by the very definition, endomorphism of the unit object. So yeah, the basic example that one should keep in mind is that if you have a finite CW complex, so in the usual topology, then we can take its suspension spectrum. We add a disjoint base point, then take infinite suspension. This is an object in the stable homotopy category, which is symmetric monoidal. So we can compute its Euler characteristic. And this thing coincides with the usual topological Euler characteristic of X, which is the sum of the signed sum of dimensions. Yeah. Of the cohomology groups. Yeah. The usual topological or the characteristic of a topological space. As one can see from these definitions, which are very, very general, and they use only this monoidal structure, that if you have some symmetric, if you have some monoidal functor between two symmetric monoidal categories, and if you have a strongly dualizable object, then its Euler characteristic goes to Euler characteristic. So if we compute first Euler characteristic inside C, and then take the image, then it goes to the Euler characteristic and inside C prime of f of x. And we will use it, of course. So yeah, this is the basic generalities, and then we wanted to apply to some specific case. Of course, to the case of stable Motivic stable homotopy stuff. So let me add a definition. I will say that smooth variety over S, smooth scheme over S is strongly dualizable if the suspension spectrum is strongly dualizable. Which lies in the stable homotopy category over S. So what are the examples of such guys? First of all, which objects are strongly dualizable? First, if X over S is proper, then X is strongly dualizable. If S is the spectrum of a characteristic zero field, then X is strongly dualizable. So every smooth variety of a characteristic zero field is strongly dualizable. If S is the spectrum of a characteristic P field, then in general we don't know that any variety is strongly dualizable, but if you invert P in the coefficients, then everything becomes strongly dualizable. Let me say that with Z and 1 over P coefficients. And by this I mean that in SH of S times Z with 1 over P. And for example, if S is spec Z, then again everything is strongly dualizable with rational coefficients. So in general, if the base scheme is sufficiently nice, then you need to invert all the characteristics of residual fields, and then it will become, the object will become strongly dualizable. So we have plenty of examples of strongly dualizable objects, and so we have plenty of things which we can try to compute all the characteristic of. And what do I mean by compute? I mean, all the characteristic is an element of the endomorphism ring of the unit. And of course, we have this great result by Morel that over a field, the endomorphism ring of the unit of the sphere spectrum is the Grothendieck-Witt group, Grothendieck-Witt ring of quadratic forms of a K. So if we are given some smooth variety, say projective or something like that, then we can associate to it somehow a quadratic form, which is its Euler, A1-Euler characteristic. And there is a number of recipes how to do this. Let me just mention one thing. I'm not going to use it, but I think that it is, I mean, it's a great computation by Marc Levine and Alexey. They show, they show, in some sense, they give an explicit answer for the computation of the Euler characteristic of a proper variety, smooth proper.
Alexey, there's a question in the chat.
Sure.
And I was going to ask why, I mean, so you use de Jong and things like that for 3 to show that everything is dualizable over characteristic field, but why does it work over Z?
Yeah, in some sense by the same reason, and it is carefully written in Ciesinski-Deglis.
Oh, okay, great. Thank you.
Sure. Yeah, I guess I should say some names for this example. For the proper guys, it is, I think, goes to Voevodsky, but it is at least over a field. But there is a very nice treatment in Marc Levine paper. For characteristic 0, there is a nice treatment of this stuff in Riu's paper. And I guess for characteristic P, there is appendix by, again, Riu in the paper by Marc Levine. And
Yang and Zhao.
Yeah, right. Let me find my note. Levine, Yang, and Zhao. Right. So let me come back to this great theorem by Marc and Reductive, that if a variety is smooth and proper, then you can canonically, and what do you need to do? You need to write down some finite dimensional vector space of K and some quadratic form on it, or bilinear form. Yeah, let me put here that characteristic of the base field is not 2. And for a proper guy, we can write down a very explicit finite dimensional space. You can just take cohomology groups of exterior powers, I mean, cohomology of differential forms. And since this guy was proper, then these guys are finite dimensional. And you can sum this over all I and j. And so, the theorem says that this Euler characteristic of X is this thing with the bilinear form given by the following thing. You take this cohomology, you take the complementary group, omega d minus j. D is the dimension of X. Then you can take the cup product, which goes to hd of x omega d. And there is the trace map from here to the base field. And this thing gives you a bilinear form on this vector space, and this is precisely the answer. So in some sense, I mean, in a very precise sense, you can write down a very explicit vector space with a very explicit bilinear form, which represents this Euler characteristic. And there are other approaches to computations of this stuff. That you can slightly massage this answer to get an answer in terms of Hochschild homology. There is a recent preprint on this. And you can also, for example, use Euler numbers of the tangent bundle to get the A1 Euler characteristic. And I should name a lot of names here, but I think that I will forget most of them, so I won't name anyone. So, but all the kind of a problem, or I mean, a problem from my point of view is that all these approaches work well. Okay, there are some questions in the chat. Let me answer them. I mean, Frederick said that X should be proper over Z, but I mean, it is from his paper, so he should be right, I guess. But I'm not sure. Yeah, the Levine-Rexed result is for proper schemes, right, Mark?
I think maybe, yeah, I think it's proper is okay. I forget exactly how we wrote it, but it shouldn't. I think we wrote it for projective actually. But
okay,
should
let me put
yeah.
Let me put projective to be on the safe side. Yeah, I thought it was proper, but yeah. In any case, I won't use it. And for this x over z, I'm not sure. I mean, for proper, everything is okay. And you don't need to take rational coefficients at all. And I mean, one should look into the Frederick's paper, into Dzieciński-Dickley's paper. Let me just put here some question mark. I had an impression that with rational coefficients, you can take anything. Yeah, constructive. I mean, the thing there that constructible guys, I mean that, okay, I don't want to go into the details, but I'm pretty sure that any x is okay there with rational coefficients. So okay, I was saying that there are a lot of approaches to computing this A1 Euler characteristics, but all of them somehow work only for projective guys or for the guys which you can take an explicit compactification, and then you just deal with this compactification, which is proper, maybe projective, and then somehow deal with this divisor which you add, and then from these answers you can try to write down the answer for the guys that you start from. And let me pose this as a question. I don't have any answer, and it would be great if someone could answer this. So suppose that you are given an arbitrary smooth guy over K, and say characteristic of K is 0. And suppose that X is affine, because I'm going to talk about affine guys later on. And the question is, are there any means to compute the A1 or the characteristic of X without looking at compactifications? I mean, in topology, you don't need your variety to be compact or something like that. to compute Euler characteristics. You just write down these cohomology groups and count their dimensions, and that's the answer. You don't need to compactify your guy. And here in Motivic homotopy, the only general recipe that we have is to compactify and then look at these projective guys. So I don't know the answer for this question, and I think this is a nice and important question. Yeah, but in any case, let me turn to, let me go further. So why should one compute this Euler characteristic? What can it tell you about the geometry or something like that? And there is another theorem by Marc, which says the following. So suppose you are given a smooth variety of a K, and suppose that you know that its A1-Euler characteristic is invertible as an element of the Grothendieck-Witt ring of a K. There is another comment in chat. I don't think that it has finite cohomology. I mean, the general problem with affine guys. Yeah, Tony says that, asks if the algebraic Deram complex have finite cohomology for affine guys. I don't think so. I mean, for affine guys, everything is usually finite dimension, finite rank over the ring. But yeah, how can you? I mean, it is finally generated over the ring, but not over the base field. That should be the problem from my point of view. So yeah, the theorem by Marc is that if you have something smooth with invertible A1-Euler characteristic, and suppose that you have some other smooth guy of a K, and suppose that you are given with a Nisnevich locally trivial bundle of a B with fiber X. Then the claim of the theorem is that if you look at the suspension spectra, you just suspend this Y to B morphism, then this map has a section. And this section is given by Motivic Becker-Gottlieb transfer. And in particular, for every representable cohomology theory, the pullback is injective. For every E in SH of K. Yes, and this can give you some kind of splitting principles. What is the usual splitting principle in cohomology? Suppose you are given a smooth variety, for example, X, and a vector bundle over X. And then splitting principle says you that there exists some morphism P, and you pull back this guy, this vector bundle along this morphism. So there is some morphism P such that P upper star is injective on cohomology or on Chow groups, if you want to stay in algebraic geometry. And this pullback is a direct sum of line bundles. So you can split without losing any information on cohomology you can split your vector bundle by a pool block to a direct sum of line bundles. And there is a very explicit version for this Y, of course, as everyone knows who knows the splitting principle. For example, you can take the scheme of isomorphism, the scheme of, say, trivializations of this vector bundle. Modulo torus. I mean, this is precisely the scheme of splittings of this vector bundle into a sum of line bundles. And let me write down some kind of generalized splitting stuff that we have from these Marc theorems. So suppose that we are given with linear algebraic groups. And suppose that the Euler characteristic of the quotient variety is invertible. Then we can form the following picture. So again, we have some x, and suppose that we are given with some Nisnevich locally trivial G torsor. Instead of a vector bundle, here we take a G torsor, right? Because vector bundles are the same as GLN torsors, and here we take just G torsor. Then the claim is that we can put here this torsor modulo H, and this is the same as Y on the left, because this isomorphism schema is precisely the GLN torsor associated to the vector bundle. And we can draw this picture. We can pull back this G torsor. And in this picture, again, P upper star is injective on cohomology, on, let me say that, on any representable cohomology theory. And second, an analog of this splitting condition is that this pullback comes from an H torsor. And by this I mean that this guy, it is in general, it lies in H1 with coefficients Ng, but this construction says that it lies in the image of H1 Nisnevich over the base G over H with coefficients in H. Yeah. So in some sense, you can reduce your, you can take a base change which doesn't forget anything about homology, and on this new variety, you can reduce the structure group to this subgroup H. What does it mean in the easiest setting? So suppose that G was GLN, similar to the classical splitting principle, and take H to be the normalizer inside GLN of GM cross N, of the maximal torus. Then GLN torsors are the same as, and there is a canonical equivalence of this notion and the notion of vector bundles. And what are these N GLN of these guy torsors? And these things correspond to the following. If it was just the maximal torus, just gm to the power n, then it would be the usual splitting principle. Then it would be a sum of line bundles. But this normalizer is slightly bigger than the maximal torus. It has also the Weyl group there, which permutes the factors on the torus. So this thing can be thought as these decompositions up to permutation of these summands. It is not very precise, but this is the thing that it means. For example, there is an étale cover which splits your vector bundle into a sum of line bundles. Yeah, so the outcome of the thing that I said here is that if you have a pair of linear algebraic groups, and we know that A1-Euler characteristic of this quotient is invertible, then we can somehow reduce the structure group from G to H.
Alexey, can I have a quick question, please?
Sure.
In your formulation, is H torsus Nisnevich locally trivial by assumption, or any H in G?
No, the point was that we start with a Nisnevich locally trivial torsor, G, and then we can try to do something with it.
I have missed these things.
Yeah, then we pull it back to something, and it of course remains to be Nisnevich locally trivial, but then over this something it can be reduced to an H torsor. Okay, so yeah, the question is, of course, for the next natural question is, for which pairs of groups do we have this assumption that G over H has an invertible A1-Euler characteristic? And there is a nice conjecture. Let me say that it is by Marc Levine and Fabien Morel. It is stated in a paper by Marc and attributed, at least in the strong form, to Fabien. So suppose that we have a split reductive group over K. K is some field. And let me put N for the normalizer of the torus, of the maximal torus. So the weak form of this conjecture is that it's precisely the thing that I was talking about, is that if you take G over N and compute its A1-Euler characteristic, then this is an invertible element in the Grothendieck-Witt ring here. And the strong form is that it equals to 1. So, and this says that you can somehow reduce the structure group from G to this normalizer of the torus. So, for example, if you had a vector bundle with some additional structure, I don't know, symplectic or something like that, then this statement says that up to some base change which doesn't lose anything in cohomology, you can think about your vector bundle as a direct sum of line bundles up to some permutation, which is given by the corresponding Weyl group. So yeah, Marc stated this conjecture in that preprint, and he proved that the weak form holds for GLN for any n, and he proved that the strong form holds for GL2. And it can be proved by very explicit geometric reasons. And there is a recent preprint by Joshua and Pablo Pelaez that the strong form holds for any G. So if the field contains the square root of -1. Yes, and I'm going to say that to tell you how to show that the weak form holds for any G without any assumption on the field. So if the characteristic is 0, then this thing holds. And if characteristic of K is P, then the same holds these Z1 or P coefficients. Yeah, and the reason, of course, is that in general, we don't know that G over N is strongly dualizable in characteristic P. Of course, it should be, but yeah, we don't know any proof for that. And of course, yeah.
Question, but once you invert P, it doesn't really change the Grothendieck-Witt group at all.
Yeah, right.
And you know that the rank is an integer, so doesn't that?
Sure. And the point is that I don't know that I can define the A1-Euler characteristic for G over N, because this object probably is not dualizable.
Ah, okay.
Yeah, and of course, yeah, and this holds integrally, of course, if we know that and G over N is strongly dualizable, precisely by the reasons that Marc says.
No, but I mean, don't you know that it's strongly dualizable after you invert P in the category?
Yeah, I know that.
Yeah, and then you get something in GW of K with 1 over P.
Yeah,
but
right.
you also know the rank has to be an integer.
Sure.
And doesn't that tell you it actually lands in GW of K?
It may, of course, it lands there, but the point is that, I mean, what do you prove by that?
Yeah, well, and it's invertible in GW.
Sure.
K invert P.
But this A1-Euler characteristic is computed in the in the category with P inverted.
Yeah, that's true.
And in general, we don't know if there is in general such an invariant as A1-Euler characteristic of G over N integrally.
Okay, great, thanks.
Yeah, if you had some, I mean, this kind of addresses that question that I posed before, that if you can somehow define some, yeah, okay, let me stop with that. Yeah, the point that in characteristic P is that we cannot write down this thing, because G of N probably is not, maybe is not strongly dualizable. Yeah, so how can one prove this? Yeah, of course, base change says base change and the functionality of A1-Euler characteristic says that it is sufficient to look at prime fields. FP and Q. So the first lemma, I may say something about it in the end if I have some time, but probably I won't have time for that. The first lemma says that if I have something smooth over Z and G over N is this guy, because everything comes from integral forms of this split group can be defined over Z, and everything inside is defined over Z, which we need. So if something is smooth over Z, and suppose that we know this thing is invertible, by this I mean that we base change to the spec Q. So this is a variety of spec Q. So suppose that we know that this guy is invertible over Q, and then it is invertible over any prime field. And again with z with 1 over p coefficients, because in general we don't know that this will be dualizable. This is the first lemma, which says that it is sufficient to look only at the picture over Q. And the second lemma, which is from that preprint by Marc, which says that suppose we have something smooth over Q, and then its Euler characteristic is invertible if and only if it is invertible after base change to the real numbers. And this is invertible if and only if the topological Euler characteristic for the complex Betti realization equals to plus minus 1, and topological Euler characteristic for the real Betti realization equals to plus minus 1. Let me sketch the proof for this. It is quite easy. Yeah, the first equivalence basically follows from the fact, immediately follows from the fact that the kernel of the map from the GW of Q to GW of R is nilpotent. So roughly speaking, the invertible elements in GWQ and GWR are more or less the same. And the second equality follows from the fact that GW of R is determined by rank and signature of the quadratic form, and the fact that rank goes to goes precisely to the topological or the characteristic of the complex realization, and signature equals to the second guy, to the topological or the characteristic of the real realization. So the outcome of the stuff that I told you is that it is sufficient to compute the topological Euler characteristics of complex and real Betti realizations of this G over N. And that is the thing that I want to do now. So the first lemma is easy, is that, and quite well known, and again it is written, for example, in that preprint by Marc, that if you look at the complex realization, then the topological Euler characteristic is 1. And the proof is, as I said, quite straightforward. So we look at this variety manifold. Since C is algebraically closed, we can rewrite this as C points of G modulo C points of the normalizer. Then it has a finite cover by G of C over the complex points of the torus. And this is a finite cover of degree which equals to the size of the Weil group. And this GC over TC is homotopy equivalent to G of C over the Borel group. Because the fibers are affine spaces, which are the unipotent radicals of this barrier group, which are isomorphic to these S varieties. And the cohomology of the last thing is very well known. As an abelian group, this guy is free with the basis given, for example, by Schubert varieties. So, and they, since we took complex points, then all these cohomology groups sit in even dimensions. Yeah. So in any case, the Euler characteristic of this guy is precisely the size of the Weyl group. And if you, so the Euler characteristic of this guy is precisely the size of the Weyl group. And then we need to divide by this number to get the Euler characteristic of this thing that we started with. So it equals to 1. Okay, that was easier. The computation for the real points is much more trickier. So again, I claim that the topological Euler characteristic of this thing equals to 1. So first of all, we need to understand what this variety is. And as it was stated in the title of my talk, this is just the variety of maximal tori. It is well known that over an algebraically closed field, all maximal tori are conjugate. And this n is precisely the stabilizer of some chosen maximal tori under the conjugation action by group G. So this means that this G over n is precisely the variety of maximal tori. By this I mean that if you want, for example, compute its points over some field, for example, then these points are precisely the maximal tori defined over this field. Again, this thing has action by G, by multiplication from the left, and this variety of maximal tori, in other language, it has the action by conjugation. I mean, the action from the left on the left-hand side is the same as the action by conjugation on this variety. So then we can take this, with this preparation, we can take real points. So again, we have an action of the real points of the group G over this variety, which we want to compute Euler characteristic of. It acts with finitely many orbits. This is a general fact for real stuff. And for example, you can see it from the long exit sequence, which has some H1 cohomology with coefficients in a Weyl group to the right, which is finite. So, and this set on the right is precisely, as I have already said, is the variety of maximal tori or defined over R. And this action is the action by conjugation of this maximal tori. So we have some finite number of maximal tori which are not conjugate. I mean, these are some representations of the conjugacy classes. Let me give you a very naive example about which you could have in mind looking at this picture. For example, if G is SL2, then of course you have over R. Then of course you have the usual split, maximal split torus, which is GM. But on the other hand, you have a compact variant of the torus, which you can write in this form, subject to the relation that x squared plus y squared equals to 1. And this is also a maximal R torus in SL2. Over complex numbers, of course, these guys become conjugate, but over the reals, they are not conjugate because one guy is, okay, real points of one guy are compact and for the other guy are not compact. So in general, some of these maximal tori that I have chosen, they are not only not conjugate, but they are also non-isomorphic. But probably there are some isomorphic guys, but which are not conjugate by matrices from G of R. So I have taken these representatives, and now I know that this variety, Gn of R, is the disjoint union of orbits of these guys. And orbits of these guys are precisely G over R, which acts by conjugation, modulo the stabilizer of this action for each guy. And the stabilizer is precisely the normalizer of the corresponding torus, the real points of the normalizer. And that's it. So now I want to compute the topological Euler characteristic of these individual pieces. And it is well known that now we are in a realm of Lie groups. I mean, the usual Lie groups, which are real manifolds and all that stuff. And one knows very well that a very important ingredient there is compact groups, maximal compact subgroups and maximal compact tori. So let me define the following numbers. The compact rank of Ti is by definition the dimension of the maximal compact subgroup in the real points of this torus. And the compact rank of the whole group G is the maximum of these guys, of compact ranks of this tori. So, yeah. For example, in my example, the compact rank of the first torus was 0, right? Because there are no positive. I mean, all the compact subgroups there are 0-dimensional. In fact, it is just plus minus 1. And here, the compact rank is 1, and the compact rank of the whole group is also 1. So the claim is that the following holds. First, there exists precisely one index such that the corresponding torus has compact rank equal to the compact rank of G. And the second claim is that the topological Euler characteristic of this quotient, of this orbit, we sliced our manifold into a disjoint unit of these orbits, and the claim is that for each orbit, the Euler characteristic is either 0 if this compact rank is small, if it doesn't equal to the compact rank of G, and otherwise it is 1. And the computations that we wanted we will follow from this, right? Because we just need to sum these topological characteristics for all these orbits. And this claim says that for one orbit it equals to 1, and for all the other orbits it equals to 0. So how one could show this claim? I won't give you any details, but let me just sketch it. The first fact follows from the well-known theory of Lie groups. It follows from the facts that maximal compact subgroups are conjugate. So we have this G of R, we have maximal compact subgroups there, and all of them are conjugate to each other. And the second is that all maximal compact tori are conjugate. So if you had two such TIs, then first we take maximal compact subgroups that contain them, then move one to another by conjugation, and then you have this tori in one maximal compact subgroup, and they are conjugate inside this by this second fact, that maximal compact tori are conjugate. So all such tori are conjugate to each other. The second part is slightly more interesting. So let me sketch it. I will sketch the computation which gives you 0. The second one is more or less the same, but a little bit more, one should be a little bit more careful. So suppose that the compact rank of Ti is less than compact rank of G. First recall that we have a short exit sequence, which takes Ti to its normalizer. I will denote it by Ni, which is this Ng of Ti. And then we have the Weyl group for Ti. And this Weyl group it is not the, I mean, it in general, it does depend on the torus, right? But in any case, it is an ethyl group scheme. And this means in particular that the index of the torus inside this normalizer is finite after taking real points. And then I'm going to draw some picture close to the one that I have drawn before. So we have G of R over Ni of R, which you want to compute all the characteristic of. Then we can go to G of R over Ti of R. And this is a finite cover precisely by this, right? This is precisely the degree of this covering. And then I'm going to use the following fact, which is also classical from Mosto 62. He says something more general that I'm going to state, but I will state it in the form which is related to the picture above. So suppose that we are given two reductive groups over R, and suppose that we have chosen maximal compact subgroups inside the real points. Then we can go from K2 over K1 to G of R over H of R, and this map is a homotopy equivalence. And in fact, it is a deformation retract. So let me do this in the picture above. So I have this K over J. It is the maximal compact subgroup in G of R. And I have the maximal compact subgroup in the torus. And then I can go from K of J. Yeah, and this is a homotopy equivalence by this fact. And then I can go from here to here. I change this maximal compact subgroup to the component of the identity. And what is this component of the identity? This is a torus in a compact group. So this is several many copies of S1. And this R is less than the compact rank of this group. This is basically the assumption that we started with. So this torus is not maximal. It is not maximal compact torus. So we can quotient out some additional S1s. To the power of compact rank of G minus R. And this is compact rank G. And this is a fibration with fiber S1 to the power of this compact rank G minus R. And this is a positive number. And recall that topological Euler characteristic of S1 is 0. So I'm finishing with this. So the Euler characteristic of this guy is the Euler characteristic of this guy times the Euler characteristic of this guy. And this one is 0, right? Because this has S1s. So this Euler characteristic is 0. And then this Euler characteristic is 0 because it was a finite covering. And this is a homotopy equivalence. So this is 0, and this is also 0. And this is precisely the statement that we wanted to have here. And for the second half is quite similar, but you need to be a little bit more careful with all these finite covers and with this map. So yeah, I have run out of time, so thank you for the attention.
Great, thanks very much. Oh, are there any questions?
I have a question.
Sure.
So can you say something how your base change trick works?
Do you mean for Z or for what?
Yeah, I mean, where you're reduced to doing like all finite fields to just doing Q.
Right, yeah, sure. So yeah, just a second. Yeah, it basically works in the following way. First of all, it is sufficient to work rationally, right? Because you know what the Grothendieck-Witt group of the finite field is, right? And the thing is here Q is invertible if and only if its rank is plus minus 1, right? Then you can work with rational coefficients. And then you can draw this picture. You can take SH of Z tensor Q. You can take SH of Q tensor Q. You can take SH of FP tensor Q. And I have X here, which I want to compute Euler characteristic of. Yeah, and what do I do next? Then I want to take the plus parts of this stuff. Which again keeps track of this rank, right? Because rank goes through this, through the plus part. So basically, I want to. It is sufficient to say that the Euler characteristic of X inside here equals to 1, right? But then you can compute the endomorphism rings of all these guys, of units and all these guys, and it equals to Q everywhere. So to be more precise, a little bit more precise, I can compute A1-Euler characteristic here of x, right? And I know that it goes to, if I go here and then here, it goes to 1. This was this assumption, okay, to plus minus 1. This was the assumption that A1-Euler characteristic over Q is invertible. So it goes to this plus minus 1, which lies inside here. But this is the same plus minus 1, which lies here. So if I go this way, then again I land in plus minus 1. And this is precisely the thing that we wanted, that rank is plus minus 1. Yeah. Roughly
What
speaking.
you're using here is that x becomes dualizable with rational coefficients.
Yes, yes, that's why I stated it there. I mean, I should look again into this Ciesiński-Deglis paper, but I was pretty sure that you don't need any properties assumptions there.
Okay, so maybe I should comment. So
Sure.
what we prove is that it's dualizable. So any the homotopy type of x of x is dualizable. So it means it's isomorphic to its bidual, but not strongly dualizable in general. And actually, what Wang Zhu said is true. If you look at the, say, complementary in spec Z of 1 point, then it will never be strongly dualizable because there's an obstruction by absolute purity. It's more or less like if you look at J lower shriek of 1, it will not be in L-adic situation. It will not be locally constant, so it's not constructible. And this is basically because Y upper shriek, J lower shriek is not 0.
Mm-hmm.
Whereas if you add this absolute purity for strong, which is true for a strongly dualizable object, it will just be 0 because it will be isomorphic to Y upper star, J lower shriek up to a twist. So it's only weakly dualizable. But if X is proper, then it's okay.
I mean, if X is proper, you don't need to take rational coefficients at all.
Yeah.
Yeah, but okay, I think that I need to look into this X.
I mean, isn't it just a question of computing the rank of the étale cohomology? I mean, the Euler étale cohomology Euler characteristic.
Yeah. I mean, you can. I think that you can do it in this way, but I mean, you need some picture of this kind.
No. I mean, why doesn't the argument over C work over FP bar, for example? Just a suggestion. Probably wrong.
No, I think it should work. I mean, I just wanted to do it this way, but probably it's sufficient just to take the étale realization of all this stuff and say that it works over C by explicit computation, and then say that they should be the same, probably. Yeah, okay. But in any case, over Q, everything should be okay. And over a finite field, there are some slight issues, which I'm sure can be resolved.
And what do you think about the Euler characteristic equals 1, the strong form? Does it look better? Do you try that?
No, but I am sure that it should be true, and I can suggest you the strongest form. Let me finish with this.
Oh, okay.
So the strongest form, I guess, should be that the class of G over N equals to the class of an affine space in K0 of var.
Oh.
I guess this should be the case.
Oh, interesting. Uh-huh.
And one can show I'm sure that one can show this for GLN, looking at this explicit compactification and stratificated and so on. At least with this explicit geometry, I can say that this is a polynomial in this Lefschetz guy. This is for sure, for GLN. And by Lefschetz, I mean the class of A1. Yeah, and the strongest form said that it should be not just polynomial, but A1 to the power m.
Oh, yeah. Oh, yeah. I guess for GL2, it's P2 minus P1, which is A2.
Right. Yeah.
Good.
Precisely.
Oh, yeah, interesting. Some other questions?
I had two. So the first was about going from a reductive group over K. Is it okay to just take the prime field in there? So, you know, I could imagine things not being split over, let's say K is just an extension of Q. You started with this G split reductive over some extension of Q, and then you reduce to Q, and a priori, I'd worry a little bit about that.
It works slightly the other way around. The point is that every split reductive group comes from a Z,
Okay.
from a Chevalier group.
Thanks a lot. So my other question was about your question. So you had this question about not going to a compactification to compute Euler characteristics. And so I could ask, what about if you allowed yourself to go to compactifications? So what would you do? Well, and from context, maybe you'd say there are these nice formulas for proper schemes, but then to get the affine part, if you want to use cut and paste, you'd wind up with the compactly supported Euler characteristic.
Right.
And so a priori, it's not even clear to me how you would use a compactification.
You should go to this compactly supported Euler characteristic, and at least over characteristic 0 field, as far as I understand, this compactly supported guy should be as far as I understand, it differs from the usual one by a power of -1.
But that's only for compact things. I mean, that's not really true. I think the point is, if you take a compactification with normal crossing divisor, then you do have a comparison where you put in this -1 instead of, it's not additive, it's additive up to multiplying by this -1. And so if you compactify your affine variety by something smooth and projective with normal crossing divisor, then you can compute the usual Euler characteristic of the open guy in terms of the Euler characteristics of the strata. But you have to, it's not an alternating sum, it's an alternating sum with this funny -1 thrown in.
Yeah, precisely.
Yeah, so that will always work if you have a normal crossing.
I mean, in that paper of that we discussed this compact Euler characteristic with compact support, then you say that you have map from here.
Right. You're right. That's right.
No, I think this is okay.
Yeah, that's okay.
So what paper is this?
No, I mean, I don't think that it is written anyway explicitly, but this basically follows from this fact that if you have a vector bundle over something, and the Euler characteristic of the sum space of this vector bundle is Euler characteristic of x times -1 to the power rank of this n. Yeah, this can be proved. First, you prove this for trivial vector bundles, and this is precisely the Euler characteristic of t to the power n. And then you use Meyer-Berry torus to prove it for every vector bundle, and then you can define. I think that you can just define this map from the K0 of the varieties to this Grothendieck-Witt stuff. Looking at the presentation of this, as the Bittner presentation of this thing.
Yeah, but I mean, not every. In what generality are you claiming the circled equation?
For x.
This one for x smooth, for any x, not necessarily projective or something like that. And in characteristic 0.
So I'm not saying how you get the. I can ask you later
Sure,
if you.
sure.
Not saying, okay.
Yeah.
all right.
Yeah. Some other questions? Okay. Well, let's thank Alexey again for a lovely talk. And we'll meet again at 3 p.m. So see you all then.